Hello, students. This is a momentous occasion because, as you can see, for the first time, I'm going to use a tablet to work a solution to one of your problems. It's time for me to stop being a dinosaur, get with the times, and that means I'm going to have, for a little while here, probably the handwriting of a 2-year-old or maybe a 6-year-old. So please cut me some slack here. The only problem I'll be working here is number 31 from chapter 20. This is the one about a quantity of gas in contact with the solid, and they're at different temperatures, which means heat will flow from one to the other. In fact, that's the only time heat flows is when you have a temperature difference between two bodies in contact. And what we're told is that we've got 1 mole of gas. So I'm going to put lowercase n sub g is 1. We always use lowercase n for the number of moles, capital N for the number of particles, which is a much, much greater number. And I'm going to be using the calligraphy pen with a rather thick line to mask my imprecise handwriting here. And same thing with the number of moles of the solid. Just 1 mole of each. And we're told that the temperature of the gas changes by 50 degrees Celsius. In fact, it's a temperature drop. So I'll say delta T of the gas, G for gas, is negative 50. And remember, even though the starting point, the reference point for the Kelvin and Celsius scales is different, the size of the increment is the same. So we could say this is negative 50 degrees Celsius or negative 50 K for Kelvin. I think that's easier. We're not told the temperature change for the solid. That's what we're charged with finding. What is the temperature change for the solid? Well, qualitatively, we know that if the gas experiences a decrease in temperature, then the solid is going to experience an increase in temperature because they will always meet in the middle. One goes down, one goes up until they reach equilibrium. One of the keys to solving this problem is to recognize, and this is probably one of the most important facts from these chapters on thermodynamics, the following. And this applies to the gas and the solid. The energy, whoa, what's that? Undo. Energy. I'm sorry, I'm writing so slow. Eventually it'll pick up speed. Energy per mole, that's of a gas or solid, per degree of freedom, which I'll abbreviate as DOF, per degree of freedom, per Kelvin, which I'll abbreviate capital K, not lowercase k. Both of those letters show up quite a bit in these chapters. Lowercase k for Boltzmann's constant, capital K for Kelvin's. It's this right here, 1/2 R. If you can remember that fact, you're going to have an easier time with an awful lot of these problems. So what do I mean by this? Just by virtue of being at a non-absolute zero temperature. So this solid here, this is a crystal lattice. We're told in the problem that the solid is an elemental solid, which is important. So it's just a regular array of a single type of atom. And each of those atoms is free to jiggle up and down, side to side, and into the page, out of the page. So that's already 3 degrees of freedom. And maybe you're thinking, well, it's not like it can only move in the X, Y, or Z axes, right? I mean, it could move at like 45 degrees between two of those axes or 30 degrees. It seems like there's an infinite number of directions in which each of these particles could be jiggling. Yes, that's true, but each of those arbitrary directions can be resolved into components along 3 orthogonal axes. That's the important point, is that they're jiggling in R3. Kind of abstract, but you can't reduce it to any less than 3 orthogonal directions or any more than that. However, in addition to the translational degrees of freedom, we call it translational because the particle or each atom can actually scoot sideways through space. There's also an energy associated with the stretching and compressing of these cartoon springs, interatomic springs. Obviously, there are not actual coil springs between atoms. It's just a little cartoon picture to help us think about the potential energy of interaction between each pair of adjacent particles. So we've got a spring, a cartoon spring that can store energy in the x direction, the y direction, and the z direction. So all told, there are actually and you know what? I don't know if I should be calling it 6 degrees of freedom. It's like 3 degrees of freedom in terms of motion, but there are 6 ways in which energy can be stored, or 6 places you can look for energy. So I'm realizing as I write this, this is probably a misnomer. I'm not sure I would call each of these springs a degree of freedom. But there are 6 ways in which you can have energy show up. Translational kinetic energy along the XYZ, and then potential energy in these springs along the 3 directions as well. And for each of those, if you raise the if you raise the temperature by 1 Kelvin, did I say Kelvin? That's because my best friend as a child, Calvin. No, Kelvin. For each of these degrees of freedom, each of these ways of storing energy, every time you increase the temperature by 1 Kelvin, each mole of substance gains this much energy. And how much are we talking? Well, R, up here, I'll remind you that capital R, the universal gas constant, I would just memorize this number, 8.31. Let's see. What are the units? I'm in my head, I'm doing PV equals nRT. So the left side is joules and PV equals nRT. That means we've got per mole Kelvin. In fact, all of this per stuff here, per mole, per degree of freedom, per Kelvin, it's kind of in the units of R here. So 1/2 of R is a little bit more than 4, right? What's 0.31 divided by 2? That's roughly 0.15. So 1/2 R is around 4.15. Let's just round it to 4 for the purposes of approximation here. So let me repeat that. If you raise the temperature of this solid by 1 Kelvin, then every mole of atoms in this solid will gain a little over 4 joules of energy. Obviously, raising the temperature should increase the energy, right? That seems pretty intuitive, but by how much? It depends on the number of ways of storing energy, for lack of a better word. And in this case, there are 6, because we're talking about a monatomic solid. And so that would mean that the change in energy, that's supposed to be delta E there, is the number of moles. What was that? Number of moles times, I'll put in parentheses, 6 halves, because there are 6 of those ways. 6 halves R times delta T. Okay? Because 6 halves R is the amount of energy. Did I misspeak a minute ago? I said, if you raise the temperature by 1 Kelvin, then for each mole of atoms, you get an additional 1/2 R of energy. I really should have said you get an additional 1/2 R of energy for each of these degrees of freedom, I'll call them. And since there are 6, you actually get 6 halves or 3 R extra energy for every degree Kelvin for every mole. So this quantity right here is really the so-called molar heat capacity, and we give it a capital C. What is that? Oh, come on. I keep accidentally tapping this button here. Capital C signifies that you're talking about the heat capacity per mole. Now, maybe you're wondering, why am I using the word heat right now? Because really, I'm talking about a change in energy. Well, that's a good segue into our first law of thermodynamics. I'm going to write that on a separate page. Can I do that? Yeah. Okay. There's a couple ways to increase the energy of a substance in this class. We're not concerned with nuclear energy or, I don't know, photons bombarding the substance. There's really just two for our purposes. You can either uh, exchange heat with the substance or do work on it. Our book uses the convention. We've got a plus sign here. So this is the work done on the substance. This is the heat transmitted to the substance. Now, in the statement of the problem, they say that this is a constant volume process. So the volume of this gas is not expanding or compressing, and solids really don't change their volume by much anyway. You have to subject a solid to an extraordinarily high pressure to change its volume by any amount. So we're not even worried about that at all. And we know that if there's no change in volume, well, there's no work being done. Bye-bye. So the energy change that I was just discussing is really equivalent to the heat. That's where the change in energy is coming from. So if this gas if this gas had a decrease in temperature, it's because it lost energy, and that energy loss was from heat being transmitted to the solid. So the solid received energy, or received heat, I should say, and the gas gave up heat. Again, the language is a little dicey. Heat is not some special type of energy, or it's not a fluid, a caloric fluid, as people used to think. It's just energy that's in transit. It's energy that's being thermally exchanged between two bodies. You know, there's those submicroscopic collisions between the gas particles and the solid particles. You can't see it as a human. You know, we don't see things on the submicroscopic scale, but we know that the reason the energy is being exchanged between these two is because of those collisions at the boundary. Okay, so capital C is the molar heat capacity. Very often in these chapters, we also deal with specific heat, which is the heat required per kilogram. So you're specifying per unit mass rather than per number of moles. Okay, but the important thing here is to count the number of ways that energy can be stored in this elemental solid. Now, for a monatomic gas over here, it's important that we're told it's monatomic because single atoms really only have three ways of storing energy. I don't like that word store, but I can't think of a better word. They can translate left, right, up, down, or into the page, out of the page. So it's those three translational kinetic energies that are associated with the energy of this gas. There's no springs here. They're not diatomic. So if we were talking about nitrogen gas, N2, which is two nitrogen atoms bonded together, I'll just, I don't know, put a little squiggle here. In addition to scooting left, right, up, down, into the page, out of the page, they could also be spinning around a couple axes and even vibrating away from each other. So there would be additional ways of storing energy. But here it's just a monatomic gas. So let me add a subscript S for the change in energy of the solid. There we go. So yeah, to tie that back to what I was saying a moment ago, I called this the molar heat capacity. I'm able to equate heat with change in energy because there's no work being done. That's what I showed you here with the first law of thermodynamics. The work is zero since there's no change in volume. Okay, now for the gas, we'll say that the change in energy of the gas number of moles of the gas, and I really should have that S for solid here, times, well, for each 1 Kelvin change in temperature and for each mole, there's 1/2 R change in units of energy per degree of freedom, but we've got 3 degrees of freedom. So 3/2. Come on. 3/2 R times delta T. And I should really call this delta T of the gas, and this is delta T of the solid over here. And of course, that means this quantity is the so-called heat capacity at constant volume. I didn't bother with the subscript over here. Usually, when you see that subscript V or P, you're talking about the constant volume or constant pressure heat capacity, molar heat capacity of a gas. And we don't really worry about the distinction for solids because the processes for a solid in this class are always constant volume. We're not talking about such extraordinary pressures that the volume of the solid, I mean, think about it. How could you squeeze an ice cube into a smaller volume? You'd have to subject it to many atmospheres of pressure. I don't know what that number is. You know, for a 1% change, let's say, in the volume of ice, that's probably requires 100 atmospheres. I really wouldn't know. But the problems we look at don't involve such extraordinary pressures, so we're not going to worry about that. Okay, and the whole idea here is that the energy of the whole system doesn't change. So the gas and the solid are not exchanging energy with their surroundings, just with one another. So delta E of the solid, this is painstaking, isn't it? It's going to get better. Delta E of the solid plus delta E, there we go. I just need to light a fire under my butt here. Delta E of the gas is 0. So we set these equal to each other with a minus sign, of course. Can I zoom in? Yeah. How cool is that you zoom in and it still looks smooth? I just find that amazing with those SVG graphical objects. What is that? Scalable vector graphics, I think it stands for. Okay. So is anything going to cancel out of both sides? Let's just go ahead and write the whole thing. NS times, well, 6/2 R is just 3R. That's got to be the negative of the number of moles of the gas times 3/2 R and delta T of the gas. By the way, and I'll emphasize this more probably in another worked solution. I don't have it in front of me, but there's a table in your chapter that gives you the heat capacities for various substances. And you can look at diatomic gases, monatomic gases, elemental solids, and all the numbers can be done really in your head just by keeping this in mind. If you can just remember that capital R is a little over 4, it's like 4.15. I'm sorry, capital R is 8.31. So 1/2 of R is 4.15 roughly. And then you just count the number of ways of storing energy and multiply that by 4.15. Boom, you've got your various heat capacities. And I should point out that only works for the heat capacity at constant volume, the molar heat capacity when we're talking about gases. So for the monatomic gas, 3/2 R, well, 1/2 R is 4.15, 3 times 4 is 12. So we know that the molar constant volume heat capacity for any monatomic gas will be close to 12. You can go to the table and find that it is indeed very close to 12. It's, you know, it's closer to 3 times 4.15. Okay, well, now we can evaluate stuff here, and this becomes easy because this number's 1, this number's 1. We can divide a 3 from both sides. Of course, the capital R divides out, and we find that the temperature change for the solid, I think all that's left is negative 1/2. 1/2 the temperature change of the gas. Well, the temperature change of the gas, if I recall correctly, was negative 50 kelvins. So the solid's temperature will increase by 25 degrees Celsius. And your book makes a big stink about how you're not supposed to say degrees Kelvin or you sound like a rube. Nobody really cares about that. I've got books written by European authors. In fact, one of them is a Nobel Prize winner. and they say kelvins. So if the word kelvins is good enough for a Nobel Prize winner, then it's good enough for me. But your book says, or excuse me, if the term degrees Kelvin, yeah. These other books say degrees Kelvin, but your book says no, you're supposed to say kelvins. Whatever, I'm not going to take points off if you say degrees Kelvin. I'll just judge you. All right, let's check the solution manual. Do they also get a temperature increase of 25 degrees Celsius? They do indeed. Bye-bye.